Namaskara. In this session we will continue our derivation process. We were analyzing the amortized cost for the Splay operations, and what we have derived is the following. The potential of the tree obtained after the Splay and before Splay, you denote them by T dash and T respectively, we have shown by straightforward simplification that is less than or equal to r dash x plus r dash z minus 2 r of x. Now we have to eliminate, r dash z, and we will eliminate it by relating it to r dash of x and r of x. So we need a relation connecting r dash x, r of x and r dash z. So you express r dash z in terms of this and then put that value over here. That way r dash z will go away and what you will have is only r dash x and r of x. That is the important point. The reason is we recursively continue our Splay operation at the new location of x. Therefore the bound, if we derive in terms of only r dash of s and r of x, it will lead to further simplification. So let us see how we do this. These are all logarithms of certain numbers. Therefore we will first look at some properties that are helpful for us in obtaining the bound. So let me redraw the picture here for t and t dash. Here I have z, y, x, a, b, c, d. This is converted to x, y, z, a, b, c and d. Okay, let us remember this, recall this picture. We need one property of the log, because r of x, r of y is sum of the logarithm of quantities. Okay, for any real numbers. Okay, a and b, a minus b square is greater than or equal to 0, or that means a plus b square minus 4ab, which is a minus b whole square, is greater than or equal to 0. A plus b square is greater than or equal to 4ab. When you take log, 2 log a plus b is greater than or equal to, we will bring that 4 on this side, would be better. Let us, x plus y whole square is greater than or equal to 4xy. Therefore x plus y square by 4 is greater than or equal to xy, and which is same as x plus y by 2 square is greater than or equal to xy. Taking log, 2 log x plus y by 2 is greater than or equal to log x plus log y. This is the important relation for any real value x and y. Okay. So, we will use this fact. Now, you see what we have here is r dash x plus. So, let us look at what is the relation between r dash x, r of x and r dash z. So, what is r dash z? See, this is r dash z, this is where you have r dash z. So, it is r dash z is log 1 plus c plus d. Okay. R of x, is log 1 plus a plus b. That is the beautiful part here. R of x is here, this is r of x, this is r dash, this is r. Okay. Now, if you look at r dash x, that is equal to log 3 plus, right, x y z 3 plus a plus b plus c plus d. Okay. So, you see that 1 plus c plus d, 1 plus c plus d plus 1 plus a plus b is obviously less than 3 plus a plus b plus c plus d. Okay. Therefore, what we have is the following, these two, here you can see log of x plus log of y, right, is less than or equal to x plus y by 2 x, right. So, r dash z plus r of x is less than or equal to 2 times log of, is less than or equal to 2 times log of sum of these two, log of x plus y by 2, x 1 plus c plus d, because r dash of z is 1 plus c plus d, 1 plus a plus b by 2, and this is less than 3 plus, which is less than or equal to 2 times log of 3 plus, because that is only 2, this is 3 plus a plus b plus c plus d by 2, that is equal to 2 times log of 3 plus, log of 3 plus is r dash x, is log of this is, sorry, this is r dash x, I am sorry, 2 times, we have seen this, this is log of, this is r dash x minus log 2, which is 1. Log 2 in the denominator goes as minus 1. Okay. So, that is equal to 2 times r dash x minus 1. So, r dash z plus r of x is less than or equal to 2 times r dash x minus 1. I can bring r of x there, therefore r dash of z is less than or equal to 2 times r dash x minus 1, 2 times r dash x minus 1 minus r of x. So, you can see that r dash of x is expressed purely in terms of r dash of x and r of x. We are going to plug in this value there. Okay. So, what is here is the expression r dash of x plus r dash of z minus 2 r of x. We will recall this. Phi of t dash minus phi of t is equal to is less than or equal to r dash x plus r dash z, r dash x plus r dash z minus 2 times r of x. But r dash z is less than or equal to this expression. So, I plug in that less than or equal to r dash x plus 2 r dash x minus 2 minus r of x minus 2 r of x. So, this is equal to 3 times r dash x minus r of x, because you have minus 3 r x, you have plus 3 r dash x and this minus 2. Okay. So, phi of t dash minus phi of t is 3 r dash x minus r of x minus 2. Now, the important point is we recursively proceed, and before that, when you are changing the configuration, okay, you are changing this configuration by some pointer manipulation, order 1 computation. Also, when you are searching for x, you would have come first to z and then to y and then to x, comparing. So, there is 1 unit of labor going down for x and 1 unit of labor for promoting x. So, you can have the unit cost defined in this way. Therefore, the actual cost can be defined as 2, where 2 unit represents the 2 order 1 computation that we are doing. For example, you are searching for x. What do you do for search for x? Start from the root and then keep going down, and first you would have come to z, then you would have come to y, and then you would have come to x. So, that has some cost, that is order 1 cost. Then this configuration t is converted into t dash in one step. Okay, that is another one. Therefore, we are going to have the actual cost for this stage is 2. The actual cost for this stage is 2. Therefore, actual cost potential difference, amortized cost for this stage is less than or equal to 3 times r dash x minus r of x minus 2 plus 2, which is equal to 3 times r dash of x minus r of x. It is only for this stage, but the same thing is going to happen for the next stage. What is happening in the next stage? What is happening in the next stage is, for example, the x which was here x, y, z, let us say z1, z2, okay. First it will go from x, y, z to x, y, z, z1, z2 will be there. This is x, because this configuration has been changed to this configuration, and you recursively apply again the splay. It shall move to 2 further levels. It will move to 2 further levels. So in this way you keep moving 2 further levels. For this stage, an identical computation, let us say this is this was the position of x, call the new position as x dash and call the new position x double dash. Therefore, what will be the cost for amortized cost for that stage? That will be 3 r double dash x minus r dash of x. For the first stage it will be 3 r dash of x minus r of x. So in this way you can go all the way up to the root. You add all of them because that is a total cost, okay. So when you add, you can see that this gets cancelled. That is the beauty of it. The beautiful part, the mathematically elegant part here is, we have represented that as a difference between the new and old position. Again, with respect to the new and old position, we will have a similar expression, and with respect to the further new to the old, we will have similar expression. When you add all of them, you are getting a telescopic sum which will cancel out all the intermediate one. Then we will have the final phi of t dash minus phi of t is less than or equal to 3 times rank of root minus rank of x. Rank of root minus rank of x is when whatever is the number or value when x started its journey, then it keeps moving up. We have an actual cost and amortized cost. When you add, you get amortized cost, the potential difference. So potential difference and actual cost is amortized cost. So this amortized cost with respect to the old and new, and again new and newer, in this way it will go. Finally, rank of root minus rank of x. Rank of root is log n, that is because all vertices are under root. The size of the subtree at the root is n, therefore this is less than or equal to 3 log n, because x may be leaf. If x is leaf, the size of the subtree is 1 and the rank is log 1, which is 0. So this could be 0 or this could be some positive number. Whatever it is, this is less than or equal to 3 log n. Okay. So phi of t plus phi of t dash plus actual cost will be less than or equal to like this at every stage. Therefore, the final tree and the initial tree the actual cost on the initial tree plus potential difference will be less than or equal to 3 log n. This is the crucial point. When you are expressing in terms of old and new, then that new become old and you get something newer, and in this way you are going to get expressions of this kind which will telescopically cancel out. The survivors are the last one, which is the root, and the first one, which is r of x. So r of x is greater than or equal to 0, so you can drop that and write less than or equal to 3 log n. So this is the amortized cost of search. Similarly, you can show that amortized cost of insert and anything, the actual cost plus potential difference will always be less than or equal to 3 log n. This is a beautiful expression for all operations. Amortized cost. Okay. The actual cost may vary, but amortized cost is always less than or equal to 3 log n for any operation, because every operation is you go down and then splay and come up. So the actual cost is cost of coming down and doing lot of splays to go up, that is the actual cost. Then there is a potential difference. So actual cost plus potential difference is always less than or equal to 3 log n. Okay. So what we have considered only the case for the transformation like this. Z y x a b c d to x y z a b c d. But there is another kind of a transformation, right? Z y, x may be on this side, so a b c. This is converted to x, y and z. Here I will have a, here I will have b. Even for this transformation we can show that same kind of an algebra less than or equal to 3 log n. Okay. So whatever is the mix happens, it is always bound by amortized cost of any operation is less than or equal to 3 log n. So if we have done some sequence of operations O1, O2, On, insert, delete, search, search, insert, arbitrary C, then actual cost will be C1, C2, etc. Cn. For each operation their amortized cost is A1, A2, etc. An. We know that C1 plus C2 plus Cn is less than or equal to A1 plus A2 plus An, but each of them is less than or equal to 3 log n, that is guaranteed. Therefore this sum is less than or equal to 3n log n. So any sequence of operation will have a cost not more than 3n log n. Each of them is less than or each amortized cost. The actual cost C1 plus C2, C1 can be anything, C2 can be anything, and then you have no control on this. It all depends on the current data structure and current operation, and then it could be any value. It is highly fluctuating and arbitrary value. We do not have a control on their values. In the worst case it can even be order n. Some of the operations can be very expensive, alright. It does not matter. I have a guarantee that C1 plus C2 plus Cn is less than or equal to 3n log n, order n log n. Therefore, by using this data structure, which is very simple to implement, for example, how is the insert routine going to insert x, yes, insert x in the binary search tree representing yes. Yes, whatever you do for insertion in a binary search tree, start from the root, keep searching for it, you will be at a leaf where you will say that this element is not there, attach to that leaf x. Same insertion in regular binary search tree. Then trigger Splay x. Insert as if you are inserting in a binary search tree. After x settling down in some place, trigger the Splay at x. Search for x. If you find x, trigger Splay from that node. If it is not there, there is a node at which you will report that x is not in the set. From that node, trigger the Splay like this. The last step will be. So, Splay routine is very simple. Insert, delete, search routine for binary search tree is simple. We are not maintaining any height, balance, color, nothing. It is just a ordinary search tree. Therefore, no overhead, no bookkeeping overhead, and all the functions and procedures are very simple, and this has a performance like the log n bound data structures. The log n bound data structures will also take n log n time for n operation. This also takes n log n for n operations, but this is much simpler because there are no constraint on the structure. All right. That is why this is called the self-adjusting trees, and Splay trees are a very important data structure illustrating the power of amortized analysis and designing the data structure with amortized cost in mind, not the worst case cost. So, I want to design a data structure and routines for the operation with amortized cost. When I have this amortized cost, my program becomes much simpler. Okay, and therefore, this is an award-winning idea. Hopcroft, Tarzan, they all got the Turing Award for graph algorithms and amortized analysis. These are all cited as the great time-tested ideas and work, and so they were honored with the Turing Award for these kind of amazing discoveries. Okay, so I will conclude the discussions on Splay tree at this point. Thank you.